Hi, I'm Radhakrishna Pillai from IIT Madras. Today in this course on basic construction materials, we are having this module on materials engineering concepts. Today we will be continuing discussing on mechanical and also on the non-mechanical properties. So these are some of the books, and today's material are mainly coming from these two books, and of course a lot of photographs from the internet are also being included for demonstration purposes. So today we will cover mechanical properties, mainly looking at brittle behavior and ductile behavior, and also looking at work and energy, fatigue failure, those mechanisms. Then towards the end we will briefly talk about various non-mechanical properties, because that is also becoming more and more important while selecting material for construction. Finally, we will just have a brief discussion on overall design concepts for selecting various materials. Now, let us look at this map, seismic map of India, where we have India is divided into 4 zones, each having different risk level. So, looking at the zone 2, which is blue color, you can see that it is of low risk zone. Then zone 3, which is moderate risk zone, yellow color. Zone 4 is a high risk zone, and zone 5 with red color is a very high risk zone. So, in India we have all these the various geographic locations, they have different hazard level for considering seismic activity. So, that means that we also have to design our structures to resist such loads. So, here you can see an example on the left side, the photograph in the red box. That is actually a multi-story building which is collapsed due to an earthquake, and people in that building did not get any reaction time to come out of the building. So, a lot of damage both for the building and also for human lives. Now, that is represented, that the behavior of that building is represented by this red curve, which is showing very brittle behavior. Okay, or in other words, the width of that graph, if you see the red graph, it is not very wide. Okay, and also the area under the graph is relatively small or less. Now, look at the green case, which is a ductile structure. Okay, you can see that this column over here at the lower floor of this building, it is actually swayed or tilted, but not collapsed. So, people in that building actually can come out after the earthquake, and it is also very clear from this photograph, it is of the same building. You can very clearly see that the columns are inclined here, or in other words they are tilted or swayed, but they have not collapsed. So, this is what we want. We want our structure to be ductile, to absorb the energy, but not reach the collapse level, or in other words a lot of energy is required to collapse the structure. So, that is our objective. We need to make our structure ductile to prevent the collapse and provide enough time to escape from the building. That is the advantage. So, you do not how do we achieve this? Okay, that is the main thing which we are talking right now, and what type of materials we should use to achieve this kind of behavior. And this is all not only for earthquake loads, but also for wind and impact load when it comes. That is also another case where we need ductile materials, so that we can save lives and also structure. I mean, even the structure we can probably retrofit that structure if it is only if it is only deformed and not collapsed. There are possibilities for that. This is another type of structure, road structure, where you can see on the left side you have a lot of cracks, okay, crack structure, wide cracks, whereas on the right side, when so the left side, the wide crack, it is mainly because of the concrete which is used, and the plain concrete is actually brittle in nature. So, it will crack, it will not bend or deform as you expect from a reinforced concrete system. On the right side, I mean, I do not know if it is a reinforced concrete or a fiber reinforced concrete, but some kind of ductile system is being used on the right side. I took this photograph from the internet. So, this ductile behavior, because of that, the road on the right side is not going to crack like you see on the left side. Or in other words, even if it is going to crack, you might see lot of smaller cracks, but not very large and wide cracks. That is mainly because the stresses whichever is developed is getting distributed because of the presence of either the steel reinforcement or the fibers, etc. Okay. So, where the more the ductile the material is, you can actually control the amount of the crack width, or crack resistance will be relatively better. Now, here is two examples of metals when you talk about brittle and ductile behavior. On the left side, you can see focus on this red box here, this red box. Okay. You can see that the shape of the bottom portion and the top portion, like these two region I am talking, it is kind of exactly, if you want to put those pieces back together, you can actually glue them together. It is not very, I mean, there is no deformation which had happened at those broken the fracture surfaces. Okay. In other words, the material did not flow, the material at the breaking point, this material here and this material here did not flow much before it fractured. That means it is relatively, it is a brittle failure. Whereas on the right side, if you look at, here you can see the material has flow, it's flowing here as you pull, it gets narrower or necking is happening. So, that kind of flow is happening because the material is more ductile in nature. Okay. So, we want this kind of ductile material so that we get enough warning before the structure collapses. So, as you see on the left side, more clearly I am going to show you, see the crack on this cast iron pipe, there is a crack going like this. Okay. Now, you can see that the pipe's cross section, if I take a cross section here, it is still going to be circular. So, I am going to draw it here, the pipe cross section is going to be circular again. Whereas, on the right side, if the steel pipe which is deformed, if I take a cross section here, it is probably going to be something like this. If you draw cross section, it is going to be something like this. So, it has opened up and deformed, whereas on the left side cast iron, which is very brittle material, it just cracked, that is all. There is no deformation to the shape of the material. So, that is a key difference between a brittle material and a ductile material. The ductile material deforms before it fractures, whereas the brittle material does not deform, it just breaks into two pieces. That is the key difference between ductile and brittle materials. Now, here it is about concrete. You can see on the first picture, it is a plain concrete with single crack and no deformation, very clearly brittle behavior, as I showed in this picture here on the left side. You can see it is see, for example, these pieces here, they are not bent or anything, they just cracked exactly where you see the cracking, and the remaining portions are still plain surfaces. Now, here look on the right side top figure, which is steel reinforcement is there, and the concrete has multiple cracks. When it is all these four images are from a flexure test, okay, or the bending test. So, you take a beam and then try to bend it, and then we see how it is behaving in the under the transverse load. And here you can see there is a deformation. So, in other words, this beam has its curve, there is a small curvature there now. It was originally straight, That is a curvature. Now, on the plain concrete system on the left side, you have a straight line here and another straight line here. So, it is more or less a V shape, whereas this is more or less a curvature shape here, and the bottom right, it is a fiber reinforced concrete where it has multiple cracks and crack bridging, because the fibers will help to close the crack or bridge the crack. It will not allow the crack to propagate that easily. It will absorb some energy and then it will prevent the crack from propagating. And also there is a deformation. You can see the shape, it is kind of a curvature. Okay, it is not a V shape like in the top left. Now, sorry, here you have a bendable concrete with multiple very fine cracks, which is sometimes very even not possible to see with your naked eyes, and these micro cracks gets bridged also because of the presence of very fine fiber material in such concrete. This is still not yet in the market a lot, probably and in the research lab. So, people are trying to demonstrate that it is possible to make very flexible concrete if you introduce very fine fibers into the concrete. And you can see deformation here also. You can see the shape is very not at all straight. I mean, it is you can see the shape of the concrete, that panel member. So, the idea here is, yes, we can make concrete which is ductile in nature by introducing steel rebars or fibers or even microfibers. Okay, it all depends on how the system steel reinforced, how the steel and concrete work as a system. Okay, now what is the whole idea when we introduce this steel into the concrete, etc.? It is mainly to make it absorb, to enable the absorption of more energy before it can fail. So, here on the brittle, the red curve on the left side, you can see this is the area under the curve, under the brittle curve, and you have another area under the larger area under the ductile curve. Definitely the one under the ductile curve is much more. So, that means that the ductile material is able to absorb more energy before it fails or before it fractures. Fracture happens here and here in these two cases. Okay. So, here also you can see brittle material, no deformation, ductile material very clearly it gets elongated and necking is happening and then eventually it fails. Now, in case of concrete, you can see that usual concrete has this green curve which is at the bottom here, whereas the fiber reinforced, FRC stands for fiber reinforced concrete, it follows a little curve, some different curve that with a larger area under the curve. So, this shaded region, the black hatch which you see, that is the additional energy which the fiber reinforced concrete is able to absorb. And you can see here there are one photograph showing the fibers inside the concrete which gets stretched and is able to absorb more energy before the concrete system fractures or fails. So, it is a more tough, the toughness of the concrete is higher, it needs more energy to break it. Now, area under the stress strain graph we just discussed, what is that indicating? It is essentially the work per unit volume of material required to deform or fracture the material, or the work required per unit volume of the material to deform or fracture. Now, in the first sketch here you can see modulus of resilience, that is essentially looking at the area under the curve until the yield point, okay, and or let us say in the elastic region of the graph. Now, when we consider also the plastic region, that is where we really look at the toughness, because we also talk about plastic movement of the or plastic deformation of the material, and until fracture you take, and that area under the curve we call it as toughness of the material. Now, there are two concepts to look at while designing the system: strength and toughness, because strength is definitely widely used parameter for designing anything when we look at collapse condition. Now, if you want to extend that collapse, even if it might even happen, because the collapse is essentially as a function of the energy absorbed. So, you have to sometimes, like the case we discussed about the earthquake resistant designs, you have to have systems with high toughness, or it should not break into two pieces until a lot of energy is absorbed. Okay, so that's the case where this one, where we look for high toughness but not necessarily high strength material. Okay, so you can look at here the second case where it is high toughness, the strength is less. Okay, so this is the delta we are talking here. This much is difference between the two materials. So even though a material will have lower strength, it can still withstand some more forces because it has larger toughness. So the energy required to break the material may be more in case of a low strength material. So in this case, as you see, low strength but high toughness. This case here, the energy under the area under this curve is more as compared to the area under the first curve here. Okay. So, we look at all these aspects when we design structures to resist earthquake or wind or impact load, etc. Toughness is very important parameter in addition to the strength.